Now we continue to learn Chapter 2, Determinants. Section 2, Properties of Determinants. And now we consider Part 3, Singularity and Determinant. First, we learn this theorem. An n by n matrix A is singular if and only if determinant A equals 0. So we see the proof, how to show this. Let U equals EK times EK minus 1 times till E1 times A be the row echelon form of A. And the EIs are all elementary matrices. So we use row operations, basic row operations to transform A to be the row echelon form U. And then we know that determinant of U equals the determinant of this multiplication of matrices, EK minus 1 till E1 till times A. And this determinant of multiplications of matrices equals the multiplication of matrices, because EK minus 1 till E1, they are all elementary matrices. So we have this property already. So it equals determinant of EK times determinant of EK minus 1 times till determinant of E1 times determinant of A. Since the determinants of the EIs are all non-zero, we learned before, we have determinant of A equals 0 if and only if determinant of U equals 0. Okay. And from this direction, if A is singular and U has a row that is full of 0, then we know determinant of U equals 0, and hence determinant of A equals 0. So if A is singular, we can have a determinant of A equals 0 by using determinant of U also equals 0. And from this direction is that we want to show if determinant of A equals 0, then A is singular. If A is non-singular, then we derive some contradiction. Okay, if A is non-singular, U is a triangular matrix with ones in the diagonal. This is row echelon form of A. So because A is non-singular, U must be a triangular matrix with ones in the diagonal, and hence determinant of U equals 1. Because for a triangular matrix, its determinant equals the multiplication of diagonal entries, all ones in the diagonal. So determinant of U equals 1, and determinant of A is not 0, which contradicts the assumption that determinant of A equals 0. Here. Okay, so we prove both directions. So an n by n matrix A is singular if and only if determinant of A equals 0. And also we can see that an n by n matrix A is non-singular if and only if determinant of A does not equal to 0. And after we learn the effects of operations on the determinants, we can have another way of calculating the determinant. Okay. So before, the only way is the definition using the cofactor expansion. And now we can do like this. We reduce A to the row echelon form. So U equals EK times EK minus 1 times till E1 times A. This means we do a series of row operations on A. If the last row of U consists entirely of zeros, this means if there's 1 0 row at the bottom of U, then A is singular. And A is singular by the theorem, we know that determinant of A, the determinant equals 0. Otherwise, A is non-singular. A is non-singular, and we know that determinant of A equals a determinant of EK times determinant of EK minus 1 till determinant of E1 inverse. Why we have this one? See from this equation, U equals this multiplication. Then, because these two matrices, they are equal, the determinants also equal. So you have a determinant of U equals the determinant of this multiplication of matrices. And then using the property that the determinants of multiplication equals the multiplication of determinants. So it equals the determinant of EK times determinant of EK minus 1 till determinant of E1 times the determinant of A. And then because A is a non-singular, then U is a triangular matrix with diagonal entries all 1. So determinant of U we know is 1. Okay, determinant of U equals 1. So immediately you can have determinant of A equals 1 divided by this determinant of EK, determinant of EK minus 1 till determinant of E1. So it's inverse of this multiplication of determinants. So we know that doing row operation is a much efficient way. So later you can compute its determinant in efficient way. Okay. We reduce A to triangular form. Actually, if A is non-singular, it is simpler to reduce A to triangular form by using operation 1 and 3. We only use these 2 operations. Thus, T equals en minus 1 till E1 times A. And hence, you can get determinant of A equals determinant of T, or determinant of T is a negative value, minus determinant of T. So because T is a triangular matrix, so it equals T11, T22 times till Tn, all is negative value. The positive sign or the negative sign is dependent on how many times you use row operation 1. Because if you use 1 time row operation 1, you will have a negative sign. If you use 2 times negative, then it's a positive sign. Okay. Here, Tii are the diagonal entries of T. Now we consider this example. Ask you to calculate the determinant of this 3 by 3 matrix. We use row operations to calculate this determinant. So say here is the original matrix, and then we use type 3 row operation first. So we use minus 2 times the first row, then add to the second row. And we also use minus 3 times the first row, then add to the third row. We will eliminate the 2-1 entry, 3-1 entry to be 0. And we find here, use the type 3 row operation. So the determinants keep the same. We just write equals here. And then for this 3 by 3 matrix, when do the determinant? We want to interchange the row 2 and row 3. Because we do such type 1 row operation, so we have a minus 1 here. And we get this determinant. And this matrix is triangular matrix, upper triangular matrix. So its determinant just the multiplication of the diagonal entries. So it is minus 1 times 2 times minus 6 times minus 5. So it's equals minus 16. Okay. So we make a comparison for 2 ways to calculate the determinant. So the number of arithmetic operations involved in the calculation of determinant by using cofactor expansion or elimination method, they are very different when n becomes larger. So when n is smaller, when n equals 2, 3, seems similar, right? They do the similar amounts of additions and multiplications, or the additions, multiplications, and divisions. However, when n becomes 10, you can see for the elimination way, Gaussian elimination, row operations, the number of additions and the multiplications and divisions are much, much smaller than that you use cofactor expansion using the definition directly. So again, we prefer the elimination way, Gaussian elimination way. So Gaussian elimination is very helpful to solve the linear system, to calculate the determinant. Okay, now we see some properties of a determinant. So the first one is about if A and B are n by n matrices, then the determinant of AB equals the determinant of A times the determinant of B. That means the determinant of multiplication of two matrices equals the multiplication of two determinants of the two matrices, respectively. Okay, let's prove it. If B is singular, then there exists non-zero x such that bx equals 0. And then we know that a times b times x also equals 0, which indicates AB is singular. So this is a property for singular matrix before we learn. So if B is singular, then there must exist non-zero x such that the system bx equals 0 has a non-trivial solution. Then because bx equals 0, if you pre-multiplying both sides by a, you will get a times b times x equals a times 0 equals 0. So AB is singular. Thus, we know that determinant of AB equals 0 because AB is singular. And because this one, determinant of B also equals 0. So, of course, determinant of AB equals determinant of A times determinant of B. Another case, if B is non-singular, then B can be written as a product of elementary matrices because after finite times of row operations, we can transform B into identity matrix. So determinant of AB can be written as determinant of A times a series of elementary matrices, A times EK times EK minus 1 till E1. And because here are all elementary matrices. For elementary matrices, we know already the determinant of A times E, elementary matrices, equals the determinant of A times the determinant of EK, EK minus 1 till E1. Right? It's just because you can think EK minus 1 till E2 as a whole first. Then this matrix and E1, when you do the determinant of this multiplication, it equals the determinant of A times till E2 times the determinant of E1. And then sequentially repeating this process, you will get it equals determinant of A times determinant of EK times determinant of EK minus 1 till determinant of E1. And later, you can also write the multiplications of those determinants of elementary matrices equals the determinant of this multiplication of elementary matrices. And this EK minus 1 till E1 is just B, because after these row operations, you can transform B into identity matrix. So B just equal this multiplication. So this is a determinant of A times determinant of B. So from this theorem, we show that for arbitrary two matrices, square matrices, its determinant of AB equals determinant of A times determinant of B. At last, we mentioned that some numerical error in determinant evaluation happens when you use computers. Because computers are finite number system, round-off errors are usually unavoidable. It is more likely that the computed value of determinant of A for a singular matrix A will not be 0, will be a small number, around 0 only.